Okay, good afternoon. So we are learning steam turbine chapter since last two lectures, and today I think we may be covering the theory, completing the theory part, and may enter into the numerical part of the steam turbines. The steam turbines, I think we have revised. It is well defined of steam turbine. Anybody of you orally or in chat box? Anybody of you? We'll start little bit revision and we'll go to a little part of the steam turbine. Okay. So nobody is defining. Nobody is understanding steam turbine. That is whether it is correct. That is nobody is understanding steam turbine is what. The steam turbine is the prime mover which converts here thermal energy of the fluid into potential energy transfer into kinetic energy, or thermal energy is converting to potential energy is in case of the water turbines. Here it is thermal energy into here kinetic energy in nozzle, and afterwards in the kinetic energy into mechanical energy. It is a prime mover type of concept. Okay, it is one of the prime mover. So working, we have discussed a lot. So it is having blades. Okay, basically nozzle and ring moving blades on mounted on shaft called rotor. One stator is there and one rotor is there. Stator having fixed blades, rotor having moving blades. The steam impact on the moving blades rotates. They are connected, they are mounted on the shaft as the shaft, as they will, it's called a rotor. So shaft will rotate, rotor will rotate. And if that rotations we carry in the presence of magnetic field, it will the EMF, electromotive force, it is current. So there are two main types of the turbines we have discussed a lot. So many times classification we have discussed, the advantages of steam turbines also we have discussed. The main steam turbine types is there, impulse steam turbine. Now, what is the impulse steam turbine? Anybody of you? From this we will revise in detail. Impulse steam turbine means which kind of steam turbine we call it as the impulse steam turbine? Anybody of you? Maybe orally by unmuting yourself. So impulse turbine means what? Only once we are converting all kinetic energy into their mechanical work, means all expansion we are carrying out in the nozzle. So afterwards pressure is remaining constant and high velocity steam is impacting on the blades. So anybody having problem? So impulse steam turbine means what? Impact is once only, we are getting impact is only once, and the fixed nozzle is there. So all pressure is expanding here. So afterwards pressure is remaining constant throughout the stages. Okay, so this fixed nozzle is there. So pressure is remaining constant here, and here the steam is impacting on the blades. So pressure only it is decreasing, the expansion of steam taking place only in nozzle. Afterwards pressure is remaining constant. So only in moving blade the steam velocity will decrease. That is the concept of the impulse turbine. Another type of turbine is what? Here reaction turbine. So without change in the pressure is remaining constant. So D-level turbine, Curtis turbine, and Retro turbines are the examples of impulse turbine. And reaction turbine, Parson turbine. So here what is happening in the reaction turbine? So partially the pressure is decreasing in the stages. So some amount of pressure is decreasing in nozzle, but afterwards all amount of pressure will not convert into kinetic energy. In the during the stages, here it is during the stages the pressure is decreases continuously. Okay, correct, very good. So I think Asmita has written. Okay. So potential energy transfer into kinetic energy, and then mechanical pressure decreases continuously. So here pressure is decreasing throughout the stages. Not only nozzle also it is decreasing, but more significant part is decreasing in the nozzle. But afterwards it is decreasing mainly in the during the stages. So in the series of the moving blades and fixed blades. So here we have pure reaction turbine is one of the concept here. High steam from boiler is passed through the moving nozzles. Steam comes out the nozzle, its velocity increases and resulting relative force. So whatever the steam is decreasing its velocity, so it is changing its momentum, because momentum is mainly depends on the velocity. As momentum is decreasing, so result change of the momentum, resultant change of that momentum is exerting the force on that particular blade. So that is the principle, Newton's second law of motion. So whenever the momentum is changing, the resultant here, there will be definitely force will be exerted on that blade, and due to that thrust or that force, here we can get the momentum, that momentum the blade will get, and it will rotate. Okay, so this is the pure reaction turbine. Then this type of turbine, alternative rows, pure impulse reaction turbine or reaction turbine, having rows of moving fixed blade and moving blade. But impulse turbine is having only one stage, and therefore we have discussed the steam expand continuously in fixed and moving blades in gradual manner, that the pressure decreases continuously. So this is the principle of behind this here, impulse turbine or reaction turbine, impulse reaction turbine. So what is there? Moving blades as well as fixed blades during the stages, not only in nozzle but during the stages also. While steam is flowing throughout the stages on moving blades, on fixed blades, the pressure is decreasing continuously. An example is our Parsons reaction turbine. So this is one of the stator is there, and the stator we are having these fixed blades. Fixed blades are acting as a nozzles only. Okay, and they or in case of the impulse turbine, if we are going for the compounding kind of methods, now I think somebody is knowing what in by compounding, etc. So in that case, yeah. Sorry, I think I have a little mess, but I was so here it is the stator. So stator of the impulse turbine is acting as the only guide blade. Okay, and stator of the impulse turbine is acting as nozzle, where the pressure is decreasing continuously and velocity goes on increasing. So it is acting as a nozzle. So the stator of of which turbine it depends. If it is a stator of impulse turbine, then this fixed stator will be acting as only guide blade. So it will guide the steam, uh, how it will effectively impact on the next stage of the moving blade. So that for that only this turbine casing here, sorry, impulse turbine. And reaction turbine or pure reaction turbine, it is acting as a nozzle. So where pressure is decreasing continuously. But this is turbine rotor where moving blades are there. So if it is an impulse turbine, then blades aerofoil shape is different. Okay. So reaction turbine, Newton's third law of motion. So fixed blade and moving blades are there, this combination. And during this area, this aerofoil shape of blades we are using. So this is a steam or gas fixed blades, vanes are there, impulse turbine. So these are fixed blades are acting as only for directing the steam in case of the impulse turbine, because this passage is remaining same, area is remaining same. Therefore, what here only it is acting as a guide blades, and it is here fixed vanes in impulse turbine. So it is only guiding the steam to impact on the moving blade. Okay, that is the purpose of the fixed vanes or fixed blades in the impulse turbine. But in case of the reaction turbine, it is acting as nozzle. So impulse turbine symmetrical blades are there. We have seen the reaction turbine blades are aerofoil, or we can say it as a aerofoil, or we can say it as a unsymmetrical blades are there. So due to that unsymmetricity, what happens here, the area of passage or area in between the two blades, passage area is definitely varying cross section, and definitely due to that pressure is decreasing continuously, and velocity is goes on here increasing. So this is going to be the reaction type of blades, unsymmetrical blades. So we have differentiate in between the impulse turbine and reaction turbine. Now here is two diagrams. Pressure variation and velocity variation is very, very important in case of the reaction turbine. So this chart, how the pressure is changing, how the velocity variation is occurring in case of the impulse turbine or in case of the reaction turbine. So here it is impulse turbine. So this is a yellow line showing the steam pressure, a green line showing the here it is going to be the velocity change. When the steam passes over this particular nozzle, or when steam passes through the nozzle, definitely pressure is goes on decreasing. So this is a yellow line is goes on decreasing definitely, and as it is impulse turbine, it remains a constant. So and when moving, it is in nozzle, what happens? Velocity is goes on increasing. So velocity when it is in the nozzle part, this is a nozzle. So this is a or chocolate or orange color here color is there. So this is a, or reddish, light reddish color is there. It is going to be here. We can say it as a nozzle where the velocity pressure is decreasing and velocity is increasing. But when steam impact on the moving blades, it loses the movement, it loses its velocity. Velocity is goes on decreasing. So finally, this much reached velocity comes to this. Okay, and this resultant change is exerting the thrust on this particular blade, so exerted the force on that particular blade, and due to that the force exerted on that blade, this blade will rotate. So that analytical part we'll see afterwards. The steam pressure is this much is the initial steam pressure, but we are decreasing this much is the decrease in the steam pressure, and this much is the velocity decrease. Okay. So, but this is a reaction turbine. Continuously the pressure is dropping. So here it is going to be the continuously this here pressure is dropping here. So this is aerofoil shaped blade. This is acting as a nozzle. So during this nozzle, what happens? Pressure is goes on decreasing and velocity goes on increasing. So this is going to be the variation. Then afterwards, in the moving blade, what happens? These moving blades are made as a acting as nozzle also, because the cross section area is goes on decreasing, and in the dynamics as the pressure here area is passage area goes on decreasing, pressure is also decreasing. So pressure decreases continuously throughout the stages, but here as it is in the moving blade, pressure of reaction turbine, pressure as well as velocity decreases. Okay, so this is pressure velocity is also goes on decreasing. So this is the basically this is difference between the impulse turbine and reaction turbine. So definitely afterwards we have gone for the comparison in between or difference points in between the impulse turbine and reaction turbine. So pressure drops only in nozzle in case of the impulse turbine. Then pressure drops continuously in moving fixed blades as well as in moving blades, or pressure drops continuously in steam nozzle as well as what in the moving blade. Then it is having symmetrical constant blade channel area because blades are symmetrical, varying blade channel area because blades are asymmetrical, aerofoil or asymmetrical shaped blades, symmetrical shaped blades, restricted round incomplete admission of steam because symmetricity, all round complete admission. Okay, diaphragm contains nozzle. Okay, fixed blades similar to moving blades attached. So fixed blades are acting as a moving blades. Okay, so that throughout the stages the pressure may decrease and velocity may increase. So as it is impulse is taking place, okay, therefore occupy less space for same power, but for reaction turbine more space is required. In initial stages, reaction turbine impulse turbines having efficiency is more, but later stages is having less efficiency. High efficiency final stages, low pressure stage reaction turbine, and suitable for small power requirements, suitable for high power requirements. Blade manufacturing is symmetrical, it's easy, is not difficult, easy. Okay, but blade manufacturing in case of the reaction turbine is going to be more somewhat complicated. Okay, so this is going to be the points. Velocity of steam is high because all amount of steam is converted, all amount of pressure is converted into kinetic energy in the admits at the impulse stage only. Velocity of steam is less. So this will be the points. So based on the classification we have discussed, then afterwards impulse, reaction, direction on the direction, radial, tangential, axial, number of stages, single stage, multi-stage, condensing, non-condensing, back pressure, pass out. So we explained everything, I think. So this is there, I think, no doubt. Low speed, high speed, depending on speed, low speed, medium speed, high speed, pressure, inlet, low pressure, high pressure, medium pressure. Okay, super critical. So, and then afterwards impulse turbine and classification. Then this is impulse turbine we have gone for. So water diagram I have seen here. This is acting as a nozzle. So in the nozzle, pressure is decreasing continuously. Afterwards, is remaining constant. Then, but press steam as the pressure is decreasing, velocity will increase here first. Okay. So during this is a passage channel where the area is constant. Therefore, both pressure as well as what air velocity will also remain constant. But at it is impulse turbine, only pressure decreases in nozzle, afterwards is remaining constant. Okay, so and this velocity is increasing in nozzle afterwards when it is moving. Okay, symmetrical blades, impulse turbine, when it is moving, so it is be continuously decreasing the velocity. And this is a decreased velocity. So initially this much is the highest velocity and this much is decreased. So resultant will be the force exerted on the blade because of the change of movement. Velocity after steam leaving this is will be the case, and condenser this will be the condenser pressure. It's exhaust pressure, this will be the condenser pressure. This will be the corresponding boiler pressure. So this is, I think, with this we have concluded this impulse turbine part. Then reaction turbine we have covered. Okay. So reaction turbine, fixed blades are acting as nozzles. I told this moving blade. Pressure decreases continuously throughout the fixed blade. I like what moving blade because of the cross sectional area. So fixed blade are acting as nozzle. So nozzle means pressure is decreasing here and velocity goes on increasing. Okay. And in the moving blade also their cross sectional area is aerofoil. Therefore, pressure decreases as well as the velocity is also decreases. So in the moving blades of the reaction turbine, pressure also decreases, velocity also decreases. Okay. Now after, but in fixed blade, pressure is decreasing, but velocity may increase because it is acting as a air nozzle. So fixed blade of moving reaction turbine or pure reaction turbine, here what they are acting as a nozzles. Okay. And moving blades, here no, as usual, pressure it may be decreasing in case of reaction turbine, but velocity is also decreasing because it is giving the pressure, whatever the momentum is there of steam is taken by or absorbed by the blades. Okay, so this is going to be the reaction turbine. So then up till now, I think any doubt? I have revised because this chapter is little bit imagine many things we have to imagine. So anything? No doubt, sir. Asmita. Asmita is no never she is in doubt. Others please reply. Prerna, others Prerna and Asmita, they are interacting continuously. Others please reply. So many 35 to 39 students are there in here, and but only 2 are replying. This is not good culture of our class. Please reply fast. Offline, maybe exam, maybe offline. If we, then we will be serious. Prerna and Asmita saying no doubt. Others please reply. Anybody from boys side? Nobody is boys representative. Okay. Then compounding of the turbine. So compounding, anybody can simplify the compounding of the turbine? Anybody of you? Compounding means what? The compounding is done only for which kind of turbine? Anybody of you? Okay. So impulse turbine, correct. Asmi, that is correct. So compounding is done only for impulse turbine. And the compounding is what? As it in case of the impulse turbine, there are no much more stages. And due to that, what will happen? Using more than one turbine. So stage, not stages, turbine, stages. Okay, good. So compounding means what? It is in case of the impulse turbine, as impulse is created at only once, therefore further stages are not there in case of the impulse turbine. Therefore, compounding is there. It is more than one stages we are expanding. And here, what if we are doing the impulse at only one stage? Then what will happen? So all amount of your pressure energy is get converting into kinetic energy, and due to that, the result output is there that this turbine will rotate with very high speed, maybe 10,000 rpm. But this 10,000 rpm speed is not suitable in the generator. Therefore, it is always expected. It is expected or desired that the speed of the turbine should be in the limit, practical limit, so that it can be coupled to the generator, and further we can create the electricity. So this is the general principle, general logic we are applying. So therefore, compounding is use of more than one stages in turbine. It is done for only impulse turbine. And impulse turbine, everything we have to reply that only the pressure is decreasing in nozzle. So moving blade and fixed blade, they are symmetry, showing the symmetry in nature. Therefore, for pressure never decreases. This pressure remains constant after nozzle. There, but velocity in moving blades, it is here decreasing because it is losing its momentum. So we have to, now there are three types of compounding methods. Now we'll mention three types of compounding method. Anybody of you? Compounding types here. So steam pressure should be very high. We are expecting in the Rankine cycle, it is operating performance parameters. So pressure, boiler pressure should be very much high. Condenser pressure should be very much low. And during this much boiler pressure too much high, condenser pressure too much less. So due to that, great more expansion, velocity compounding, pressure compounding, correct, and combination of that. So combination of that, it is pressure velocity compounding. Okay, so velocity compounding, pressure compounding, and pressure velocity compounding. These are the three methods of compounding of steam turbine. On that day, we have taken it very partly. So I have not. So need of compounding, the steam velocity and therefore turbine speed will be tremendously high in case of the impulse turbine. Such high speed will create high centrifugal force, which cannot cause structural failure, which can cause the structural failure. Okay, such high speed turbines cannot directly couple to generator, and reduction gearing is necessary. Gearing is reduction. Gearing is reduction speed is necessary. Okay, and with single stage exit velocity is high, also high, which is one kind of the loss. So exit velocity is very much high, but we are not using that velocity. This is one kind of what? Very loss. So practical, whatever the practical is there, that we have to go for. So for that, what we have to do is that we have to absorb some of the energy of the steam during the stages. And for that, we are going for more than one stages in case of the compounding. So that our purpose is to absorb velocity, either velocity or pressure or both of them. Depending on what things we are absorbing, which parameters we are absorbing, depending on that, compounding is in three types. One is velocity compounding, second is pressure compounding, and third one is what? Pressure velocity compounding. So velocity compounding, what we are doing? So velocity compounding, we are doing that. Here it is a nozzle. Always remember that this nozzle is acting as what? Nozzle is there. Afterward, there is a set of reduced velocity, correct? So afterwards, this is here moving blades are there and fixed blade. So fixed blade in compounding, their purpose is what? It is impulse turbine fixed blade. So fixed blade there only to guide on the next moving blade, to guide or to make the proper impact of the steam jet on the next set of the fixed blade. So for that only these moving blade, these fixed blades are used. So these are acting as a guide blade. So these are acting as a fixed blades are acting as what? Guide blades in case of the impulse turbine. So they are only directing the steam and it is impacting on the moving blade. So here in case of the velocity compounding, only nozzle pressure is decreasing. That we have to remember. So pressure is decreasing in nozzle. Okay. So this graph is very much important. Afterward, this is remaining constant. Pressure is dotted line remaining constant. So as pressure is decreasing, velocity will increase. Okay, it is increasing in the nozzle, but when it strikes on the moving blade, it is decreasing. So this is a pressure is constant, therefore velocity will also remain constant in the fixed blade. Okay, then next moving blade set, the velocity is remaining changing, decreasing, and afterwards again moving fixed blade, it is remaining constant because pressure is constant. No change in pressure, no change in velocity, and afterwards again, so this much is a decrease. So this much velocity we got in the nozzle. So afterward, this much is the, and this is the final velocity. So this is a velocity reduction. So this much is the, if velocity, and this much velocity of the steam leaving the turbine, okay, or entering to the condenser. So this is the velocity. So velocity we are decreasing continuously as pressure is remaining constant. Therefore, our velocity, by arranging more number of rows of moving blades and fixed blades, and that is fixed blades are acting as only guide blades. Understand this velocity compounding. So in your drawing, you can draw this particular figure. I will give 5 minutes. So let us, this is very important. Understood? Any doubt? I think on last lecture also nobody was having doubt. Now I think they may not also. In short language, I mean here, understood, sir. No problem, Asmita. You're always understanding, but still others, please, anybody having doubt, please reply. And draw a diagram. Uh, okay, 5 minutes I am giving to you so that it may practice, because when we are watching the diagrams, etc., initially we feel that we are understanding, but here it may, Ganesh Gaudi very good. So it Abish, okay, very good Ganesh. So, but when we draw after some time, the knowledge is quality. Therefore, some little bit practicing also we have to go for, because the concept to make pure sound, solid sound concept, if you want, then some writing or some drawing is very much required in association or along with our regular listening. Please reply after your diagram gets over. Oh, Rasmita, okay, thank you. Others please reply so that we'll go to next slide. Others reply. Okay. So when we'll draw is when then only we'll understand again. Confuse only we'll understand. In velocity compounding, only one set of nozzle, only one set because we are absorbing only velocity. Purpose is not absorbing pressure. If you want to absorb pressure, we have to go for more and more, more than one, two or more rows of nozzles. But here only one nozzle, but two or more rows of moving blades, and in between that there is also row of fixed blade, fixed guide blade. So it is very important. Impulse turbine fixed blades are acting as only guide blade. Pressure is remaining constant and velocity is also not decreasing, remaining constant. Velocity, these blades are used to only guide the velocity, the guide blades only give a direction of steam towards the moving blade so that it will effectively impact on the next stage of the turbine. So velocity compounding example is Curtis turbine. So Retu, Curtis and D level turbines are the examples of impulse turbine, and out of that Curtis turbine is the velocity compounding is done for that Curtis turbine. Now pressure compounding. So what will be pressure compounding? What we are absorbing in pressure compounding? Anybody of you? As name itself is there, it is a pressure compounding. What do we have to absorb? We are not interested to absorb velocity. We are in velocity will be definitely, but what? Continuously we have to absorb the pressure absorbs. Okay, very good. The pressure is absorbing, and for that we have to do is what? Very more than one set of nozzles we have to do. So this is going to be nozzles are there. Okay, this nozzle set is different fixed here. So this will be acting as a fixed blade now. This is acting as a nozzle. Okay, this is nozzle means shape is like asymmetrical, and here moving blades, here moving on the moving blade, pressure is here remaining constant because it is impulse turbine moving blade. Here the reaction turbine moving blade, still the pressure is also decreasing continuously, and also velocity is also decreasing in moving blades. So this is nozzle, this is will be also nozzle part. Fixed blade are acting as nozzles, moving blades. So in this nozzle, pressure is decreasing. Afterward, during this moving blade stage, it will remaining constant. Okay. And next fixed blade, next nozzle, again the pressure is goes on decreasing, but again on the moving blade it will remain constant. Okay, but this pressure will decrease from this to this, and moving blade nozzle velocity goes on increasing in the nozzle. Okay, and then when it is moving blade, it is decreasing because it is losing the movement. Fixed blade again it is nozzle because nozzle, therefore velocity will also increase, and here moving blade again this will be what? Increase. So this is the air velocity, final velocity, okay, in nozzle, and this is decreasing, but pressure is decreased continuously, so that output, whatever the velocity we are getting, so this is output velocity will be also less. So we are dragging or we are absorbing energy, either maybe pressure or either maybe velocity, so that at the output here we can get the controllable velocity. So this is the pressure compounding. More than one nozzle is used. So here number of simple impulse turbine stages arranged in series. Fixed blade act as the nozzles. Okay, and these are the here means more number of nozzles in are there. As pressure reduces gradually, specific volume generally increases and blade height. So, but here remember that nozzle means pressure is decreasing continuously in the nozzle, and here at the, our intention is that velocity of steam at output chart here it should be very much less. This is the pressure compounding. Again, I give 5 minutes to you. Please draw it and tell me over if it goes. So you can use two color pens if possible, one for pressure variation and one for velocity variation. Two color coding if you are using, it will be good. Anybody over? Asmita, somebody or other Prerna, others please reply. I am tracing on this because this is a very important pressure compounding. Pressure is absorbing more than one set of nozzles are used. This may be the highlighting points. Number of impulse turbine stages arranged in series, no problem. Fixed bed acting as nozzle that increases steam velocity by reducing pressure. As pressure generally decreases, specific volume decreases. So decreasing. And another stage is there. It is going to be what combination of pressure and velocity. So both pressure as well as velocity we have to absorb continuously for during this particular stages. And for that, what we have to do? So we have to, for decreasing pressure continuously, we have to arrange more than one set of nozzles. So this will be one nozzle. Afterward, this is going to be the fixed blade. They are acting as a. So these are the fixed means we have to consider this as a fixed means guide blades. In between the two moving blades, whatever the blades are there, so that blades we call it as a. So I think this we are not covered on that day. So pressure velocity both we have to absorb pressure as well as what velocity. So this where the symmetricity fixed blade is there, where the symmetry in between these passages is the same area, moving blade passages remain same area. So this is going to be the fixed blades of the impulse turbine. So this is acting as only guide blades. G I can write guide blade. And this whatever this is the cross section area, it goes on decreasing. This is acting as a nozzle. So this is hatched lines are there. It is going to be acting as a nozzle. So this is one nozzle. This is another nozzle, and if it is the third nozzle. So in the nozzle, pressure is decreasing. Now we go for pressure variation, dotted line. So here pressure is decreasing. Okay, in nozzle. Afterwards, it remaining constant through the first stage. This is going to be the first stage. Okay. Throughout the first stage, this pressure is goes on. Pressure is remaining constant. Next nozzle, the pressure is decreasing continuously. Okay. And afterwards, again next stage, it will decrease. It will remain same. Again in the nozzle, next nozzle, again this pressure will be goes on decreasing. So pressure is decreasing in the nozzle, but during the moving travel of the moving blade and guide blade or fixed blade, during this stage, it is remaining constant because it is a impulse type of turbine. Then here in the nozzle, what happens? Same principle. Nozzle, what will happen? The pressure velocity goes on increasing. But when moving blade, the velocity is remaining, the velocity will decrease because it is striking and it is giving its momentum. Afterwards, fixed blade, as it is the fixed pressure is remaining constant, the velocity how to be remain constant because it is the fixed blade of the impulse turbine. And then moving blade, again it will decrease. Okay. And again it will increase because next is the nozzle. Okay. So this is going to be nozzle. Afterwards, symbolically, significantly, it will increase. The moving blade decrease, remaining constant in the fixed blade. Moving blade again it decrease, and again the nozzle it will increase. Okay. So this will be increase. Okay. So this next stage we are not considering. So, and due means we are decreasing pressure as well as we are decreasing the pressure as well as the velocity as well as pressure. So, decreasing, this is the output. So, where pressure and velocity both are absorbed continuously. Pressure is absorbed continuously by arranging increasing number of nozzles, okay, series of nozzles, and here by increasing number of wing blades, we are decreasing the velocity. So this is the combination, both were absorbing, it is pressure as well as velocity. So combination of pressure and velocity compounding, pressure drops divided into number of stages. Also velocity is obtained in each stage, absorbed in several stages. So this is going to be the velocity compounding of the pressure velocity compounding. So by arranging them different nozzles, pressure is continuously decreasing throughout the stages. So this is, and by arranging more number of sets of moving blades, the velocity is goes on decreasing. This is the combination of what both pressure and velocity compounding. Both were absorbing. Yes. Okay. Anybody have doubt? Please draw diagram. So let's bit. Anybody in doubt, etc., you can ask. Understood if you can write. Please mention in reply. It's been understanding. If anybody have doubt, voice side. So I want some prerna is also understanding. Others please reply. Is called as pressure velocity compounding. So this is the first stage. During first stage, when pressure decreasing up to first next stage, pressure is remaining same. So this is the first stage. This is the second stage, and this is starting of third stage. But I think it is incomplete. So if we don't want to draw this nozzle, don't draw this nozzle. Why? Because next is again we have to increase the pressure. Okay. Then your first stage, then second stage, and next is condenser. Here third stage. If the again one more nozzle is used, then this is here this set. After that again one set of moving blade, fixed blade, moving blade. This is one set. What is that? First set is that nozzle. One set is there. It includes nozzle, then moving blade, fixed blade. Fixed blade is acting as what? Guide blade. Then again moving blade. Again, this is one set, and this set will repeat. N M wing fixed wing nozzle. Puna फिर here approach again N, again M, again guide blade or fixed blade, and again F. This is N M F N N M F M N M F M. That is to note the coding. Guide blades or fixed blades of the impulse turbine are acting as a guide blades, fixed blades. So I have given near about 1 hour to revise this again. One things. The steam turbine is little bit complicated. Imaginary things are more. Mathematical part will start now. For it also some graphical methodology is there. Understood pressure compounding, velocity compounding, draw diagram. Now I think we'll stop this here. We'll go to next presentation. Now we have to go for the so this is the velocity triangle, velocity diagram. So we have to go for the steam tables. Now some are the moving blades. Those blades are moving. Some blades are attached to the stator. Okay, to stator means those are connected to direct mounted on the rotor. This is the rotor. This is, we can call it as a rotor here, shaft. Okay, some blades, moving blades, are attached on this particular rotor. Okay, and fixed blade, they are connected only to the casing. So this is the one of the pictorial view of the wheel. So this is a compact only fixed blade, moving blade, and steam is impacting on the blades. So it is a tangential direction is impacting. So now here one impulse turbine. So we'll take example of impulse turbine and we'll continue. This is same is continued. Same practice is going to be continued for the reaction turbine also. So now some whatever why I stopped last presentation, sharing of the last presentation, because in some of the books, maximum some of the books, some of the IIT professors, they have used a V symbol, V as a velocity for the steam. Okay, so V is the symbol for the velocity, and some books are there, rare books are there, where I told you to refer Aryado. They have used C as a symbol. Therefore, to have this particular less confusion, because generally in our notebook, etc., we're using C as a symbol because Aryado is one of the book where we're using C symbol for the velocity. Okay, and the blade velocity, the symbol is U. It is constant in all books, but P and C, there is going to be some books there used the velocity of T here C, some have used the velocity V. Okay, now this is the blade. Now we have to understand very clearly, concentrate. So this is going to be the axial direction, is here. This is the axial direction along the axis, and this is, let us consider this is a blade, rotor. Okay, and this is going to be connect. This is a blades, moving blades. Okay, let us consider this as a moving blade. Okay, now this is the direction of rotation. This, in this direction the rotor will rotate when the steam. Now this is one nozzle, and from the nozzle the steam is impacting on the blades. Okay, now this is impacting on the tangential direction. So tangential means this is tangent to this particular thing. So this is let us consider this point. So from this air nozzle the steam is coming. Okay, so this is impacting on this particular nozzle. So this is C1. Okay, and in this case the blade will moving with velocity U. Okay, so this blade will move in this direction. So direction of rotation will be in this direction. The blade will move, and steam will come in this direction. So there is here it is going to be C1. Okay, so blade is resultant velocity coming from the nozzle. So this C1 and this U is having here relative velocity difference. This is a relatively they are differ. So this is a C1 and this is a U, and this is called as, so what are this vectorly, if we join them, so this C1 and this is CR1. Okay, so this is CR1. This is, don't consider this as C1. Okay, this is CR1 and this is will be C1. So this difference is called as CR1. It is called as relative velocity difference. Now here suffix 1 is used for inlet velocity triangles. Inlet, what there is the, what are the components are there of velocity? because in turbine the input and output were counting in terms of velocity, because pressure is decreasing. So we are interested in kinetic energy, how the kinetic energy will convert into mechanical energy, that only how the force is generating, how the momentum is generating, or how the momentum is producing, so that the force will be exerted or work will be done by the turbine. So here input velocity triangles are there. Input inlet, or you can call it inlet or input inlet. The suffix is going to be one, and outlet, when the blade, the velocities will really exit from this particular blade. So that outlet triangle is there. It is called out when it is going to be outlet. This outlet is denoted by suffix 2. So due to when the steam is impacting tangentially here on this particular blade, okay, this is a impulse turbine work setting, therefore these symmetrical blades are there, cross section, and this will increase. Okay. Now when this particular blade will leave this particular leave, so it will leave in this direction. So leaving direction is here when it is leaving. So it will come with this direction, and it at this tip it will leave. And here in this case, when it is leaving, so this is going to be a C2 is going to be the resultant velocity at leaving. So absolute, we can say it is absolute velocity of steam at outlet. Okay, and this velocity here, this velocity, this will move in the upward direction. When so this will be rotation in the, this is in the upward direction. This is the velocity of u in this direction. We can measure and we can put this velocity as a u. Now again there is a, in this C2 is going to be more here. C2 is going to be less, because why? C1 is less more and C2 is less because momentum, steam has lost the momentum. So therefore the component is decreasing, and this C2 and this U, again there is one relative difference at outlet, that is called as what? CR2. This is called as what? CR2. That is a relative velocity difference at outlet. So at this is a condition outlet. And now here, now I am trying to this explaining you one or two times so that we will not understand at once. Okay, so this resultant component is there of the steam. Okay, maybe at inlet and maybe at outlet. This is having only two components. So one is what? It's one is C vertical component is there, and one is in tangential direction. One component is there, and it is called as CW1. Okay, it is called, due to that only the whirling action is taking place. So this is C, okay, C1, and this C1 is having two components. One is in tangential direction. Now afterwards we are changing the direction. So this is a, हे आपण जरासा उभा पकडला ब्लेड असा, वर्टिकल अँगल 90 डिग्री नंतर चेंज केला आपण, वर घेतला, वर्टिकल केलं हे computer. Then in that case, this will be acting as a tangential direction. So this is the horizontal component of this C1. आता इथे दिसताना तेवढे आपल्याला इथे दिसताना आपण this vertical distance, CF1. So horizontal component of this C1 is called as whirl component, and this component, या C1 चे जे दोन component आहेत यातला एकच component फक्त काय करतोय, आपल्याला त्याला blade वर impact करतोय. One is only responsible for flow. So the vertical component ह्याच्या जर tangential direction च्या जर ह्याच्या tangential ला, ह्याच्या direction च्या tangential ला जर ह्याचा horizontal component जर बघितला, horizontal component is responsible या blade च्या horizontal, blade च्या tangential direction ला तर जो component हा आहे, this component is what? Responsible for whirling action. Therefore this is called as what? CW1 component. It is called what? CW1. Okay. Okay, and one component is there which is vertical. त्या component ला perpendicular. It is called what? Flow velocity, flow component of velocity, flow component of steam at velocity. And this component, flow component of steam at inlet, and this component is responsible to get the flow of steam throughout the turbine, to get the flow of steam throughout the turbine. So one is one in vertical direction, okay, and one vertical direction is what? C the F1, and it is here horizontal tangential direction is going to be the CW1, and this CW1 is responsible for getting the work. Similarly here, C2 is having two components here. One is in this direction, C2 च्या डायरेक्शन जे असणार आहे तो त्या CF2 ह्या फक्त हा CF2 फक्त फ्लो साठी वापरला जातोय CF2, आणि ह्याचा जो हा कॉम्पोनंट आहे व्हर्टिकल, हा इथे दाखवला गेलेला नाही, इथे इनलेटला पण दाखवलं नाही आपण, तो ह्याला म्हणतोय आपण CW2. Okay. Now here there are two angles are there. Oh, that is, one is what nozzle angle, it is alpha. It is what alpha is what nozzle angle. So nozzle angle little bit, nozzle angle is alpha. So this alpha one means what? It is a nozzle angle at inlet. So alpha one is what? It is a nozzle angle at inlet. So what this particular C1 is max angle with the horizontal is called as alpha. Here what the C2 is max angle with the horizontal or tangential direction. Okay, so that is called as alpha 2. Okay, so alpha 2 means this is alpha 2 means this is tangential direction. Okay, so this is called as alpha 2. This is nozzle angle at outlet. Okay, then here this is beta. This is blade angles. Blade angle is what? Beta is there. So this is a blade angle. So this is beta 1. Okay, so whatever this particular CR1 is max angle with this particular blade, this is called as what? Beta 1. And CR2, whatever it is making angle with the tangential direction, so that is called as what? Beta 2, blade angle at outlet. So now actually it is little bit complicated, not that much easy to understand here. Okay, but I'm trying to give you that first only understand the terminology of this particular diagram. So this is going to be the rotation of the blade. Some components are tangential, some components are perpendicular to tangential direction. Now here inlet components are denoted by suffix 1. Basically we'll start with that. Outlet components are, they are starting with 2. The C is related to the steam velocities. Steam velocity means what? Tangential velocity, flow component of steam. The whirl component means what? Which is making the whirling or working action of that particular steam. This is called a whirl component. It is denoted by CW1. CW. It is denoted by C suffix W. If it is CW1, it is whirl component of steam at inlet. It is whirl component of steam at outlet. And one is CF1, whirl component, whirl flow component of steam at inlet, and flow component of steam at outlet. Okay. Then alpha 1 is the nozzle angle at inlet, alpha 2 is nozzle angle at outlet, beta 1 is blade angle at inlet, and beta 2 is blade angle at outlet. So this is going to be the here pictorial view, 3 dimensional. Okay. Now here we have to draw the velocity diagram. For them we have to simplify the diagram, and this is going to be the our simplified diagram. So simplified diagram, it takes that this is nozzle. So this nozzle makes angle with the horizontal. Now we have made this with 90 degree. So this is nozzle. From the nozzle, the steam is coming in this direction. This is the absolute component of steam is coming in this particular direction. Okay, and whatever this alpha 1, so this is a parallel lines are there. So this angle, so this is going to be this angle, and this angle is going to be equal. Okay, so this angle and this angle. So this alpha 1, this is a whatever the C1, this is C1 means what? Absolute velocity of steam at inlet. And whatever this angle, this C1 is max angle with the horizontal direction, tangential direction, right? Tangential direction. So this is called as alpha 1. Okay, here, and this is with this. So here, this blade is moving in this direction now. This blade is moving in this particular direction. Okay, due to that impact, and this is called as what? U1. So this is will be the U1, U1. Okay, or U1 is equal to U2. Afterwards, we'll get it. So U, okay, with this velocity, U velocity, the blade will move. Okay, and with them, the C1 and U, whatever difference is there, so that component we call it as a CR1. So this is the what dark line is there. So this is going to be our inlet velocity triangle. So this CR1. So CR1 means what? It is the relative velocity at inlet. So relative means what? Relative difference in between C1 and U. याच्यामध्ये काय relative difference and this is what? Relative velocity component of steam at inlet. And this is whatever this angle is, this C1, CR1 is making angle with this tangential direction, horizontal direction is called as beta 1. It is called as blade angle at inlet. Now this C1, whatever this velocity is coming from, absolute velocity is coming from nozzle, having two components. One is what? Horizontal component or tangential direction component. It is called as CW1, which is responsible for making the action, whirling action of that particular blade. If फिरण्याची action आहे, जे momentum, rotary momentum आहे, it is going to be CW1. And one is there, it is going to be vertical component is CF1. So it is velocity of flow at inlet, and this component is only responsible to get the flow. यातला C1 मधला काहीच पार्ट म्हणजे horizontal part जे tangential direction चा only responsible for getting the flow, and remaining flow vertical component is there perpendicular to CW1, it is called as CF1. So this will be the here responsible for getting the flow. Okay. Similarly, these components will be what? This will be the velocity. Less velocity will be there. It is going to be C2. Okay. And this C2 is nothing but what? Absolute velocity of steam at outlet. So this C2, whatever is making angle with the horizontal, with tangential direction is called as alpha 2. Other angle, this will be called as what? Alpha 2. It is nozzle angle at inlet. Okay. Now this C2 is having also two components. One is in tangential direction is called as CW2. C2 is a tangential component, the horizontal component CW2, and C2 is a vertical component. It is called as what? CF2, velocity flow at outlet. Okay, and has C2 and where this U is remaining constant. So this will be moving with this velocity only, U velocity. This C2 and this U is also having some relative difference, and it is called as what? CR2. And whatever this CR2 makes an angle with the horizontal is called as blade angle at outlet. Now everybody understand this here. It is peripheral velocity or tangential velocity. It can be obtained by equation U is equal to pi dn divided by 60. So it is rotary motion, we can convert into tangential direction. Pi dn divided by 60. Okay. Look, let us go. We will not go to directly in that case. Now, first of all, you have to understand the diagram. So everybody understand this nomenclature. This is a blade moving with velocity U. Okay, it is a peripheral velocity. Okay, the steam is coming from this nozzle. It is moving with velocity, coming with absolute velocity C1. So this C1 is having two components. One is in the direction of blade velocity, U tangential blade velocity is called as what? Which is responsible for making action of that particular blade, rotation of that blade is called as here UCW1. म्हणजे ह्याचा vertical component पण आहे हा इथपर्यंत C1 चा horizontal पण त्या ब्लेडचा ह्याला आपण horizontal म्हणूया सिम्पली भाषेत CW1, and ह्याचा vertical जो आहे तो CF1. So this absolute velocity is making angle with the tangential component of blade, that is called as what? Alpha 1. Tasa C2 jasa it makes an angle with the tangential direction of blade. Blade direction is tangential आहे. This is angle making an angle alpha 2 with the horizontal. Okay. Then this C2 is having also two components. In whirl component direction, it is CW2. In here whirl flow component, vertical direction component, perpendicular to CW2 is flow component. Flow component is responsible for getting only flow, and whirl component, part of that absolute velocity, which is responsible for making the whirling or rotating action of that particular steam. And okay, and there again this will move with the velocity U, and U C2 and U मधला जे velocity difference त्याला आपण CR2 म्हणतो. इथं पण C1 आणि याच्या मधला जो velocity difference आहे त्याला आपण काय म्हणतो? CR1. आणि हा CR1 जो ब्लेड ची रिलेटिव्ह आहे, ब्लेड कंपोनेंट आहे, तो हा whatever is making angle with horizontal is called as beta 1. It is called as blade angle at inlet. And here CR2 तसाच CR2 जे आउटलेटला ब्लेड अँगल horizontal चे अँगल करतो त्याला आपण म्हणतो ब्लेड अँगल at outlet. Now everybody, at least everybody know that normal terminology and what are the means components, CR1, CR1, their direction and nature. Everybody might be understand. Please reply. Yes, sir, understood, Asmila. Thank you. Others, please reply. Little bit applied mechanics word used. Prerna and okay, understood. Others, please reply. I will give 10 minutes to you to draw this, because this is very, to solve the numericals, we have to use this methodology. Okay, but otherwise, now as in both triangle, okay, we'll go to that. Then we'll here both triangles we are having what here common factor is u. U is there. It is going to be blade velocity is going to be common. See, blade is only common. So this blade is common for both. Here also u, here also what u. Therefore, we can to simplify the diagram, we can here couple this combined velocity diagram, where this u is common, velocity is going to be what, u is going to be common. This is a common blade velocity is common. Okay, and from that the C1 makes an angle. So this C1. So otherwise, I will go for. So whether this screen is visible all? Whether this screen is visible? Yes, thank you. Okay. Now I will. Yes, thank you, Ganesh. Now what we'll do is we'll draw the combined velocity diagram, where velocity is common in both triangle, inlet triangle as well as outlet triangle, is going to be u. So therefore, what we are going to do is u, this u. Okay, so afterwards I will. This is u component. Okay. Now this u is going to be the blade velocity, and is common for both triangle. So if you observe here, both it is going to be common. So this is therefore it is called as combined velocity diagram. U is going to be common, and from this u here, the velocity which is coming is absolute velocity. Okay, and which is making angle alpha 1 with the tangential direction, horizontal direction. This we call it as a C1. It is absolute velocity component of stream. Okay. Absolute velocity component of steam at inlet. Now, whatever this U and C1, they are having this relative difference is there, and that we call it as a CR1. To make this diagram simplified, what we are doing is here, this U and C1, they are having here, this will be U velocity is moving in the direction. The C1 making an angle alpha 1 with the horizontal is called as nozzle angle at inlet. So this is CR1, and whatever this CR1 makes angle with this tangential direction, that we call it as a beta 1, which is blade angle at inlet. Okay. Now, this C1 is having two components. I told you this C1 is having what? Two components. One is what? Flow component, which is now in this tangential direction. Have blade jet direction must tell component y. It will go if I will draw, I will write the projection in the direction. This C1 is having two components. This will be called as what? CW1, which is responsible to get the whirling action, rotation action of that particular blade. It is called as CW1. Okay. And this one is their vertical component, which is responsible for making the flow. And this is called what? Vertical component. It is called what? CF1. Okay. So this is written part is not visible. Not visible. Written part is not visible. Now it is visible. Is it visible now? Now visible, na? Okay. I will erase and I will draw again because my intention is there so that I will draw. It is okay. Okay. Let us assume that here the blade is common. Blade is velocity is going to be common in both. Therefore, U is going to be common. Okay. Let us assume that the nozzle is in the direction here from this here nozzle is there. Is the steam is coming in the direction. Let us this will be the absolute velocity component of steam at inlet, and whatever this C1 makes angle with the horizontal or tangential direction, that we called as a nozzle angle at inlet. It is called as alpha 1. Okay, this is blade velocity component. Okay, now this U and this C1, they are having one some relative velocity difference, and that we denote by letter here CR1. This will be CR1. And this CR1 makes angle with the same U direction, the blade velocity direction, and tangential direction to the blade. That we call as a blade angle at inlet. It is called as beta 1. Now this C1 is having two components. So this C1 resultant velocity or absolute velocity is having two components. One is in perpendicular direction and one is in tangential direction to the blade. The blade is a tangential direction of that we call it as a Here it will be, this will be the flow component which is coming in the downward direction. Same as CF1, and it's now if you join this will be definitely 90-degree angle, and this component, this C1 चा हा काय झाला horizontal किंवा ब्लेडच्या डायरेक्शनला असणारा जो floor whirling component is going to be responsible for whirling action. This will be what? CW1. CW1. So C1 चे दोन component आहेत, CF1 vertical component and CW1 is going to be the horizontal component of that particular here horizontal tangential component which is responsible for the flow. So this CR1, whatever it makes angle with the horizontal is called as C1. Now from this CR1, same is resulting into CR2 because this blade is going to be give the reflecting there, and this will be the CR2. So this, and what are this CR2? CR2 is now, this is the inlet velocity triangle is completed. Now this, with this U here, what we have to draw is now our outlet of the triangle, because now from the blade only, from this only CR1 only, CR2 will result, and whatever this CR2 makes angle with the again blade tangential direction, it is called as blade angle at outlet beta 2. Now this U1 and CR2 is also having some relative difference. कशामधला असणार आहे, काय असणार आहे, तसा C1 मधला तसाच, म्हणजे this is called as what, या दोघांना जॉइन केल्यानंतर जो कंपोनंट आपल्याला मिळतो, that we called as a C2, there is absolute velocity of steam at outlet, and it is denoted by letter what, alpha 2. It is denoted by letter what, alpha 2. Okay, this is C2. Okay, this is alpha 2, blade angle at out, nozzle angle at outlet, and C2, whatever this angle here, C2 makes angle here with the tangential direction is called as alpha 2. Again, this C2 is having what, two component. One is what, now this C2 is in this direction. Now C1 is in this direction and C2 is in opposite direction. So this C1 is also having two components. So जो vertical, जो त्याच्या direction ला, tangential direction ला जो आहे, is going to be what? If I will draw this, okay. So this tangential हा direction हा कुठे आहे, इकडे आहे, आणि याची CW1 ची direction इकडे आहे. So CW1 and CW2, C2 चा जो horizontal ह्याला काय म्हणतो आपण, CW2, and ह्याचा जो vertical component आहे, so same direction, flow direction, which is responsible for flow, is called as CF2, which is called as what, flow component of steam at outlet, CF2. Okay, and याचा resultant आहे, both are in opposite direction, so resultant काय असतो आपला, याच्या सगळ्यांचा दोघांचा मिळून resultant जो आहे एकदम whirling जे आहे, जे ज्याला काढतो आपण CW, and it is nothing but equal to what, CW1 and CW2. This is common velocity triangle diagram. This is alpha 1 is nozzle angle at inlet. Sagra nomenclature I have defined. How these are representing? This is going to be combination diagram, and with the help of numericals, we have to draw the diagram graphically with scale, and we'll get all the components. Or trigonometry, we have to use, either we have to use the trigonometry, or we have to use the graphically, we have to draw the diagram for a particular numerical, then we'll get the sense of this. Okay, so this will be the, you can now draw this diagram. Understood? First tell me, understood, or you can draw the diagram, and if understood, please draw the diagram. Now draw the diagram. Understood, and draw diagram. So understood, sir. Okay, thank you, Asmita. So draw diagram. This diagram is drawn because you will understand this. Please reply. Only Asmita understood. If we want next, because this is very important. Draw diagram with scale, with pencil and scale, so that we will understand. Because I have drawn freehand scale, like freehand scale. Therefore, understood. Please reply. Only Asmita understood. Others, please reply. Prerna, Ganesh Gawali, those are interacted at least in today's class. Prerna, Ganesh Gawali, yes, sir, understood. Very good, Ganesh. Prerna Varkade also understood. Very good. Good, good. And others, please, Abhijit Babar also understood. Okay. Draw diagram this with scale so that now there is Okay, here one condition is there that CR1 is equal to CR2. There is no friction, so there is no relative motion at inlet and outlet. So motion is going, both components are same. There is no relative difference in between inlet and outlet velocity. Therefore, CR1 is equal to CR2 in this case. So where there is no friction, assumption is there that no friction, therefore this B and F, they are at the same height from BC is equal to EF in that case, or in that case CR1 is equal to CR2. हा जो CR1 जेवढा आहे थोडा जर आपण CR2 काढला तर there is no friction, so in that case it is called as blade coefficient. It is called what, the ratio, the blade coefficient is there, it is going to be letter denoted by letter B. K, okay, so K is equal to what? CR2 upon CR1. CR2 upon, it is called as blade coefficient or friction, blade friction coefficient. Blade coefficient or friction coefficient, CR2 upon CR1. If it is no friction is there, then K is equal to 1, and in that case CR1 is equal to CR2. So in that case, this height, both inlet and outlet velocity triangle, their height is, that is BC and EF, both is going to be same. But if there is little bit difference in between them, then if CR2 is not equal, velocity diagram showing effect of friction. So if the friction is there, then that CR2 is not equal to CR1. In that case, CR2 is equal to what? K into CR1. So I have defined K is equal to CR2 upon CR1. So therefore, CR2 is equal to K into CR1, and friction is there, then the friction coefficient will be K. In that case, then this diagram will not be equal. So height of inlet triangle will be having more height, outlet triangle is having less height. So this is a case. Same diagram is there. Only thing is there that CR2 is not equal to CR1 in this second case. Only this thing is there. So this is called as what? K CR2 is equal to K CR1. Same principally, but only BC is having more length. BC is here having more length than EF. Okay, and this will be the here nature. So there, all the CW1 and CW2 are going to be equal. Now, understood? First, tell me. Otherwise, so this is our. I am going to upload this PPT maybe today or tomorrow on our group. If you understand, therefore I request you to draw. Understood? Please tell, or others. Okay, Abhijit, many have understood. So this Asmita understood. Please reply and please draw. Rirna understood. Okay, Asmita over. Now we'll go to next. Okay, let us. Okay, now here from this, which component is going to be responsible? So FT, that is a force on the blade and work done by the blade. And for that, what we are going to use is FT. F is equal to M into A. So generally force is equal to what? M into mass of the steam, mass flow rate into acceleration. So acceleration is nothing but what? Here it is going to be change in velocity. Okay, and change in velocity in that direction will be here CW1 and CW2. Now here Ft is equal to, in that case, CW1 m dot means velocity or flow rate. Ft is equal to tangential force exerted on the blade by the steam. M dot is equal to, in bracket, CW1 plus minus CW2. Okay. Now here, when both are, actually it is what? M into A. So Ft is equal to what? Actually, Ft is equal to M. Okay, let M into CW1 minus CW2. But if you observe them here, if they are in opposite direction, CW1 direction is this direction and CW2 direction is this direction. Therefore, both are in opposite direction. Therefore, CW1, we can say, minus of minus, because both directions are going to be CW2. And in that case, Ft, the tangential component of force, will become what? ft is equal to what? Is equal to m into, in bracket, cw1 plus cw2, plus minus minus will become plus. So in that case, ft, this is the ft, tangential force exerted on the blade, ft, cw1 plus cw2. Okay, now when both are in same direction, sometimes maybe situation is there that cw1 and cw2 are in same direction. In that case, what will happen? Cw1, this minus sign will be there. So this is f cwm into cw1 minus cw2. Okay, so this is related to this. Okay, now the work and power, work is equal to, here work is equal to, in that case, m ft is equal to ft into u, ft into w is equal to f into s, w is equal to f into, we know that w is equal to f force into displacement, and displacement in that case it is displacement divided by time is equal to velocity. So therefore we are getting power. So this will be m ft into u is equal to m dot into cw1 plus cw2 into u. This will be watt. Okay, and if you want to convert, this will be cw1 and cw2, we are considering it as a sometimes in the, so in this is watt, this if you divided by, this will be 1000 kilowatt. So this will be, in this case it will be m into m dot